Hi students, in this session we are going to discuss the topic a complex Fourier spectrum. Complex Fourier spectrum. Simply we call it as Fourier spectrum. Fourier spectrum. Okay. Today we are going to discuss about the topic complex Fourier spectrum, or simply Fourier spectrum. What is a Fourier spectrum of a periodic signal x of t? What is Fourier spectrum of a periodic signal x of t? Simply, the Fourier spectrum of a periodic signal x of t is nothing but the plot of a Fourier coefficients versus a frequency, that is omega here. Okay, simply the plot of the graph between Fourier coefficients and frequency, that is angular frequency omega, is nothing but Fourier spectrum. So the first point, Fourier spectrum of a periodic signal x of t is nothing but plot of Fourier coefficients, versus plot of Fourier coefficients versus frequency, that is nothing but omega here. So frequency, that is omega. So the plot of a Fourier coefficient versus frequency will give the Fourier spectrum of a periodic signal x of t. And this Fourier spectrum, it is of two types. First one is amplitude spectrum, and the second one is phase spectrum. Okay, phase spectrum. What is amplitude spectrum? Simply, what is amplitude spectrum? So the plot of amplitude of the Fourier coefficients versus frequency will give the amplitude spectrum. The amplitude spectrum is nothing but the plot of amplitude of Fourier coefficients, versus frequency. Okay, so the graph for these two will give the amplitude spectrum. In the same way, what is phase spectrum? The plot of phase of Fourier coefficients, versus frequency. If you call it as angular frequency, I simply calling it as frequency. If you want to call it as exactly angular frequency, that is simply omega. So the plot of phase of the Fourier coefficients versus omega will give you the phase spectrum. Okay. So the combination of these two plots is known as Fourier frequency spectrum. Okay, the combination of these two plots combinedly will give Fourier frequency spectrum. Of the periodic signal x of t. So this combination of these two. Okay, so the two plots combinedly will give the Fourier frequency spectrum, and this type of representation is nothing but the frequency domain representation. This type of representation is nothing but frequency. This type of representation is nothing but frequency domain representation. frequency domain representation, because we are drawing the graph with respect to frequency. That is, here we are plotting the Fourier coefficients with respect to first frequency. So at what frequency, what will be the value of Fourier coefficient? That is what we are drawing the graph. So we are drawing this with respect to frequency, hence it is nothing but frequency domain representation. In generally, in time domain representation, we will draw the graphs with respect to time, but here we are drawing the graphs with respect to frequency, that is omega or omega naught, with respect to frequency, omega, or we can sometimes call omega naught. With respect to frequency, we are drawing this one. Hence this is nothing but frequency domain representation. Okay, frequency domain representation. Now this frequency spectrum exists. This frequency spectrum exists only at discrete frequencies. Important. This frequency spectrum exists only at discrete frequencies. Discrete frequencies, that is n omega naught, that is n omega naught, where n equal to 0, 1, 2, 3, so on. Okay, so this Fourier spectrum exists only at discrete frequencies. Discrete frequencies means n omega naught, where n equal to 0, 1, 2, 3, that is, first consider n equal to 0, that is frequency is 0, omega naught equal to 0. So first point. Next, n equal to 1, that is omega naught. N equal to 2, that is 2 omega naught. N equal to 3, that is 3 omega naught. That is, we have the frequencies at 0, omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on and so on. So for that reason, we are having the values only at discrete frequencies. We don't have the continuous values at all frequencies. We have the values of the signal only at discrete frequencies. Okay, discrete frequencies. Hence, this type of spectrum is called as discrete spectrum. Hence, this type of spectrum is also known as discrete spectrum. Discrete spectrum. And generally, we will get some lines at the discrete frequency. At discrete frequencies, we get the lines for amplitude or phase. Okay, we get the lines for amplitude. Hence, this type of spectrum is called as discrete spectrum or line spectrum or line spectrum. Okay, discrete spectrum or line spectrum. So this Fourier spectrum exists only at discrete frequencies like n omega naught, where n equal to 0, 1, 2. That is, it exists, it does not exist continuously. It exists only at 0, omega naught, 2 omega naught, 3 omega naught, 4 omega naught. Hence, this is this type of spectrum is known as discrete spectrum, or it may be called as line spectrum. Another name of this Fourier spectrum is discrete spectrum or line spectrum. Okay, so this is about Fourier spectrum and the types what we have in that. Okay, now we will see the Fourier spectrums for three types of Fourier series representations. That is, we have three types of Fourier series. First one is trigonometric Fourier series, next cosine form or polar form of Fourier series, and then exponential form of Fourier series. So we will see the Fourier spectrums of each one. Okay, here the small one is the trigonometric Fourier series. If you alter that one, that is alternate form of the trigonometric Fourier series is nothing but the cosine form of Fourier series, or simply the cosine form of Fourier series is an alternate form of trigonometric Fourier series. So both are almost same. Just we want to change the one form to another form. Just we will change the coefficients. Okay, we will if you take the properly the coefficients, then we get this cosine form of Fourier series from trigonometric Fourier series. Okay, I will explain each one. We all know the trigonometric Fourier series representation equation. So the trigonometric Fourier series representation is x of t equal to small a naught plus summation n equal to 1 to infinity a n cos n omega naught t plus b n sin n omega naught t. So we all know the trigonometric Fourier series representation. Trigonometric Fourier series representation. Okay, so In trigonometric Fourier series, a representation of a periodic signal x of t, trigonometric Fourier series representation of a periodic signal x of t, it consists of sine and cosine terms. Sine and cosine terms with positive and negative amplitude coefficients. Positive and negative amplitude coefficients, but with no phase angles. But with no phase angles. Here in this trigonometric Fourier series representation of the signal x of t consists of sine and cosine terms with positive amplitude coefficients, positive and negative amplitude coefficients as an and bn, but with no phase angles, that is, in this trigonometric Fourier series we have the positive and negative amplitude coefficients like an and bn, but with no phase angles, we all know the equation, that is x of t equal to a naught plus summation n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. There the coefficients an and bn are the trigonometric Fourier series coefficients. Hence in this trigonometric Fourier series consists of sine and cosine terms with amplitude coefficients as an and bn, that is they have the both positive and negative amplitude coefficients as an and bn, but with no phase angles, that is there is no phase angle. Hence for trigonometric Fourier series we can draw the amplitude spectrum only, okay. For that reason we are going to the next one, that is cosine form or polar form of Fourier series. Simply it is nothing but the alternate form of this trigonometric Fourier series. Simply this cosine form is nothing but the alternate form of trigonometric series. That is, here we have to change these coefficients and we have to represent this cosine form completely in cosines. Here in trigonometric we have sines and cos, here we have only cos values. Simply we all know the cosine form representation of a periodic signal x of t will be given as x of t equal to capital A naught plus summation n equal to 1 to infinity capital an cos of n omega naught t plus theta n, where this a naught and an are the Fourier coefficients of this cosine form and theta n is the phase angle, okay. So this cosine form of representation of a periodic signal x of t consists of only positive amplitude coefficients, that is this an is positive. Why? Because here the value of an is nothing but square root of an square plus bn square, so square positive, square root of positive is a positive. Hence this under a naught will be equal to small a naught, and here the capital A naught will be equal to small a naught, an equal to square root of an square plus bn square, and phase angle theta n equal to minus tan inverse of bn by an. So by this conversion I can get the cosine form of Fourier series from trigonometric form of Fourier series. Just using these conversions I will get this. Hence it is nothing but the alternate form of trigonometric Fourier series. That means in this alternate form of trigonometric series, or in this cosine form of Fourier series, I have only the cos terms with positive amplitude coefficients. That means this cosine form or representation of a periodic signal x of t consists of only positive amplitude coefficients and with phase angle and with the phase angle. Here we have the phase angle, whereas in trigonometric Fourier series we doesn't have the phase angle. So in cosine form representation we can plot both amplitude spectra and phase spectra. Here we can draw both amplitude spectra and phase spectra. Amplitude spectrum and phase spectrum, that is the graph drawn for the amplitude coefficients versus frequency will give amplitude spectrum, and the graph drawn for phase coefficient with respect to the phase of the coefficients with respect to the frequency will give the phase spectrum. Okay, so this one here, this we will get the amplitude coefficients only for the positive frequencies. In this we get the amplitude coefficients only for positive frequencies, that is we have the coefficients for positive frequency, that way we can draw the graph only for one side, hence it is called as single sided spectrum. This one, this cosine form, here it is called as single sided spectrum. Why? Because in this cosine form representation the amplitude coefficients exist only for positive frequencies, frequencies, hence we call this as an single sided spectrum. Okay, now the last one, third one, so that is nothing but exponential Fourier series. Exponential Fourier series. The last one is exponential Fourier series. Okay, so in this exponential Fourier series, will have the Fourier coefficients as Cn. It has an amplitude coefficient as Cn, which is a complex one. This this complex Fourier series, will have an amplitude coefficient Cn, which is complex. That means it has both magnitude as well as a phase. Since the Cn, the amplitude coefficient, the coefficient of this exponential Fourier series, there is a complex exponential Fourier series. In this complex exponential Fourier series, the coefficient is Cn, which is a complex one. So in exponential Fourier series, the Fourier coefficient is Cn, the amplitude coefficient is Cn, which is a complex one. That is, it has both magnitude and phase. It has both magnitude and phase. Hence, we can draw magnitude spectrum as well as phase spectrum for this exponential Fourier series. Already we all know the exponential Fourier series of a periodic signal x of t. That is simply x of t equal to summation n equal to minus into infinity Cn e power j n omega naught t, where that Cn is the Fourier coefficient. That Cn is a complex value. That is, it is having both magnitude and phase. Hence, we can draw both magnitude spectra as well as phase spectra. So for this, I can draw the magnitude. Hence, we can draw the magnitude spectrum, which is nothing but the mod of Cn versus frequency omega. So this will give the magnitude spectrum. In the same way, I can draw the phase spectrum. So phase angle, that is phase angle of this Cn versus frequency. This will give the phase spectra. That means we can plot both magnitude spectra as well as phase spectra. And here the coefficients, these Fourier coefficients or the amplitude coefficient, these coefficients exist for both positive and negative frequencies. Here the coefficients, the amplitude coefficients exist for or simply the Fourier coefficients exist for both positive as well as negative frequencies, positive and negative frequencies. Hence, this type of spectrum is called as two-sided spectra. So this is an two-sided spectra. So the exponential Fourier series is a two-sided spectrum, or you can call it as a double-sided spectrum. Whereas this cosine form Fourier spectrum is a single-sided spectrum or one-sided spectrum. Here the exponential Fourier series, the Fourier spectrum is a two-sided spectrum or double-sided spectrum. Why it is called as two-sided? Because here the Fourier coefficient, the coefficients will have the values for both positive and negative frequencies. For both positive, and we have the values of both for positive and negative frequencies. Hence we can go for this two-sided spectra. So this in this exponential Fourier series, the Fourier spectrum is called as a two-sided spectra. Okay. Now we all know Cn in general is a complex number. Cn is a complex number. So Cn can be represented with some magnitude mod of Cn into e power j theta n with some phase angle. So we know that Cn is general as a complex number. In general, we call it as, we'll represent it as a complex number. So Cn is some magnitude into e power j theta n. Now, this coefficient exists for negative frequencies also. Okay, that is C minus n. C minus n. C minus n will also given as mod of Cn into e power minus j theta n. Into e power minus j theta n. That means the magnitude of Cn and magnitude of C minus n are same. So what we can write, that is magnitude of Cn is same as magnitude of C minus n. Both are same. Hence for Cn and for C minus n, I write an mod Cn. So the magnitudes are same for positive and negative. Hence this magnitude spectrum is symmetrical about the vertical axis. Magnitude spectrum is symmetrical about the vertical axis. And see, for phase angle, for Cn it is positive and for C minus n it is negative. So the phase spectrum is anti-symmetrical about the vertical axis. From this I can say the magnitude spectrum is symmetrical about the vertical axis and phase spectrum is anti-symmetrical about the vertical axis. Now I will go for the spectrum of this alternate form of trigonometric Fourier series and exponential Fourier series. I will show you the spectrums, graphical representations, spectrum of this another form of trigonometric Fourier series, that is a cosine form of Fourier series and exponential Fourier series. I will give the spectrum of these two. Now we will see the spectrum of a cosine form or alternate form of Fourier series first, and then we go for the spectrum of complex exponential Fourier series, that is the complex Fourier spectrum. Next, first, so here in cosine form or the alternate form of Fourier series, we have the Fourier coefficient as an and the frequency as omega. So I will go with respect to the amplitude spectrum, that is yes. Here it is a single-sided spectrum. Why? Because the Fourier coefficients exist only for the positive frequencies. Only for the positive frequency, that is 0, omega naught, 2 omega naught, 3 omega naught, and omega naught. For only positive frequencies, I will get the spectrum. Hence it is called as single-sided spectrum. Okay. So at this one, let us consider at this point, let us consider the value something like a naught. Value a1, A2, A3, AN. So you can write like this also. Okay, so even 4 omega naught, A4, whatever it may be, you can go like that. So if you go for one more thing, A4, here we get 4 omega naught. The values are so on like that. Okay, simple. Okay, so this is the spectrum of cosine form or alternate form of trigonometric Fourier series. Alternate form of trigonometric Fourier series. So simply we go on for the plot of amplitude of this Fourier coefficients with respect to the frequency omega. So I go on for the Fourier coefficients versus frequency. Hence it is the spectrum of cosine form or alternate form of trigonometric Fourier series. See, this having the Fourier coefficients only for positive frequencies, positive omega naught, 2 omega naught, 3 omega naught, 4 omega naught. Hence this type of spectrum is called a single-sided spectrum. In the same way, we can go for the spectrum of complex exponential Fourier series. So in that we have the Fourier coefficients for both positive and negative frequencies. Hence the type of spectrum is called as two-sided spectrum, or double-sided spectrum. That means there. So here the frequency is for both positive and negative. Hence I have to write the line at the middle. So this one, okay, this is 0, next omega naught, next 2 omega naught, next 3 omega naught, and so on, and next n omega naught. In the same way, minus omega naught, minus 2 omega naught, minus 3 omega naught, and so on, minus n omega naught. So here the Fourier coefficients exist for both positive and negative frequencies. Hence we can plot the spectrum for both positive and negative frequencies. Hence it is called as a two-sided spectrum or double-sided spectrum. Okay, two-sided spectrum. That means here we have to consider magnitude, that is mod of Cn. So the graph versus Fourier coefficient Cn versus omega. Okay, will give the spectrum of complex exponential Fourier series. So here the value of this one. The value of this one, treat it as C0, C1, C2, C3, Cn. So for negative frequencies also you can get the Fourier coefficients as for negative frequencies also we get the Fourier coefficients as, see this one, at minus omega naught, we have C minus 1, at minus 2 omega naught, we have C minus 2, and at minus 3 omega naught we have C minus 3, and at this point n omega naught we have C minus n. See, here we have the Fourier coefficients for positive frequencies as well as negative frequencies. Hence it is a two-sided spectrum, and this is nothing but the spectrum of complex exponential Fourier series. Okay, so already I said this magnitude spectrum is symmetrical. Magnitude spectrum is symmetrical about the vertical axis. Symmetrical. So if you fold this one with respect to the y-axis, we'll get the same thing. We'll get the same thing. Why? Because the magnitude of Cn and the magnitude of minus Cn both are same. I have shown you. So both are same. Hence, if you fold this with respect to the y-axis, we'll get the same thing. Hence, this magnitude spectrum is symmetrical about the vertical axis. Important. So here in this, because our topic is complex Fourier spectrum, so complex exponential, I consider the complex exponential Fourier series. In that I get the Fourier spectrum. That Fourier spectrum is nothing but the complex Fourier spectrum. There we have the magnitude spectrum and phase spectrum. In that the magnitude spectrum, spectrum is symmetrical. About vertical axis. Is symmetrical about vertical axis. Okay. In the same way, if you go for the phase, that is for positive Cn we have theta n, and for C minus n, that is for Cn we have theta n, for C minus n we have minus theta n. That is phase spectrum. Phase spectrum is anti-symmetrical about vertical axis. That is anti-symmetrical about vertical axis. Simply, this magnitude spectrum exhibits even symmetry, because if you fold this along with vertical axis, I will get that one, that is x of t equal x of minus t, even symmetry. And this phase spectrum exhibits odd symmetry because it is anti-symmetrical about the vertical axis. So simply here the magnitude spectrum exhibits even symmetry and the phase spectrum exhibits odd symmetry. So this is completely about the complex Fourier spectrum. So we can go for the complete analysis of this complex Fourier spectrum. Okay. So summary of today's class. Yes, I will go for the summary. So summary. In this class, first I started with the Fourier spectrum. What is Fourier spectrum and what are the two types of Fourier spectrums we have? Amplitude spectrum and phase spectrum, and then frequency domain representation. And another name for Fourier spectrum is line spectrum and discrete spectrum. After that, I explained you the Fourier spectrum or the trigonometric Fourier series representations and the coefficients present in that. And then I gone for the cosine form or alternate form of trigonometric Fourier series, and then I gone for the exponential Fourier series. So this trigonometric Fourier series, we have cos and sine terms. We have cos and sine terms with both positive and negative amplitude as an and bn, but with no phase angles. So I left it. And next I gone to the cosine form, alternate form. I changed the trigonometric Fourier series somewhat, and I get the alternate form of cosine. Alternate form of trigonometric Fourier series as cosine form of Fourier series. So there we have the Fourier coefficient, that is positive amplitude coefficients as capital AN, positive amplitude coefficients with phase angle. We have the positive amplitude coefficient. Amplitude coefficients are positive with phase angles. That is, we have both the amplitude spectrum and phase spectrum. So in that I had drawn the amplitude spectrum for that one. Okay. Next I gone for the complex exponential Fourier series. So there we have the Fourier coefficient of Cn, which is a complex one. That is in terms of both magnitude and phase. Hence we have both magnitude spectrum and phase spectrum. Okay. In cosine form the Fourier coefficient exists only for the positive frequencies. Hence it is called as one-sided spectrum, and I shown the spectrum of this cosine form or alternate form of trigonometric Fourier series. And in complex exponential Fourier series, the Fourier coefficients exist for both positive and negative frequencies. Hence, we can plot the graph for both positive and negative frequencies. Hence, it is called as two-sided spectrum. And I shown the spectrum of exponential Fourier series or spectrum of complex exponential Fourier series. So there, I consider the values of Cn. Cn is nothing but magnitude of Cn into e power j theta, whereas C minus n is nothing but magnitude of Cn e power minus j theta. Or simply, that is, we can say magnitude of Cn is same as magnitude of C minus n. For that reason, this magnitude spectrum is symmetrical about the vertical axis. That is, it exhibits even symmetry. Whereas phase spectrum is anti-symmetrical about the vertical axis. That it exhibits odd symmetry. So this is completely about the Fourier spectrum, simply complex Fourier spectrum. With this, we finish the topic Fourier spectrum. This is today's class. Thank you one and all.